Hey guys, welcome to our first video about molecular geometry. Molecular geometry is really important. We'll spend actually quite a bit of time on this because the shape and the bond angles of molecules has a lot to do with their properties, both their physical and chemical properties. Okay, so to think about molecular geometry, we're going to keep coming back to this model. It's called the Vesper model, which stands for Valence Shell Electron Pair Repulsion model. And what it basically says is that electron pairs repel each other. Now that's common sense, right? Electrons are negative. And so when you have electron pairs close to each other, there is going to be some repulsion. And to minimize that repulsion, those electron pairs are going to arrange in whatever geometry gives them the most distance from each other, gives them maximum bond angles. Now, if you did this lesson with me in class, then you can kind of just fast forward and watch again. But if you weren't in class with me, I would really recommend that you gather up some marshmallows and toothpicks, or gumdrops and toothpicks, or grapes and toothpicks, to build the models as we discuss each one, because geometry is really best understood if you can build and if you have a tactile experience with them. Let's start with methane, CH4. So again, if you're doing this for the first time, I want you to pause the video and try each step on your own. The first thing I want you to do is write your Lewis structure or your Lewis electron dot diagram for methane. So pause and do that. And this is what you would come up with. So now I want you to take a handful of marshmallows, 5 marshmallows and 4 toothpicks, and I want you to build a model of this, keeping in mind that the electron pairs that make up each bond, here's a bonding pair, etc. I want you to spread those bonding pairs as far apart from each other as you can. So when we did this in class, most people came up with this model, which in fact looks a whole lot like the electron dot diagram. But now I'm here to tell you that these bonding pairs can actually spread farther than 90 degrees from each other. So take another go at it, recalling that the molecule doesn't have to stay flat on the paper the way we draw it in a Lewis electron dot diagram. So if you take a little time with that, you can see that the bonds can actually go farther than 90 degrees. I'm putting them at about 110 degrees. But then the next bond must also be 109.5, and notice that, see how I'm not staying two-dimensional? So each bond angle needs to be 109.5, and when you've arranged all 4 of them, you get a structure that looks like this. This took me a little while to put together. So 109.5, and let's see, there's that bond angle. Now I'm going to this one, 109.5, and now I'm out here at this one, 109.5. No matter how you move the molecule, any 2 bonds are separated by that same maximum distance of 109.5. And this unique structure that maximizes 4 bond angles is known as the tetrahedron. So when we have 4 electron domains, that term electron domain is referring to a pair of electrons. So a bond is an electron domain. When you have 4 of them, the geometry is tetrahedral with 109.5 degree bond angles, and the molecular geometry has the same name, tetrahedral. It is 3-dimensional, it's not flat. Okay, we're going to keep going. The next molecule that I want you to consider is ammonia. So NH3. I want you to draw the electron dot diagram. And this is what you would come up with. And now I want you to focus your attention on the central atom, the nitrogen. And again, the same VSEPR model applies. So we want our electron pairs to arrange themselves in the geometry that gives them maximum bond angles. Okay, we have 3 electron pairs that are participating in as bonds, but we have a 4th electron pair that is a non-bonding pair or a lone pair. Okay, so nitrogen still has 1, 2, 3, 4 electron pairs. And that means that it's going to assume the tetrahedral geometry with 109.5 degrees. So take another set of marshmallows and put your 4 toothpicks in the tetrahedral arrangement. But this time, only 3 of those toothpicks are bonds. And the 4th toothpick, the 4th electron pair, the 4th electron domain is not a bonding pair, but a lone pair. So I'm going to put this non-bonding pair on that 4th toothpick. I know it looks a little bit like an alien. So when you have an electron pair that is a bond, that electron pair is in a tug of war between the 2 atoms. And the electron density is concentrated along the internuclear axis. That's the case for each of these bonding pairs. But in the case of the non-bonding pair, the electron pair is not in a tug of war between 2 atoms. Instead, it belongs exclusively to 1 atom, which means it has freedom to take up a little bit more space. And that's exactly what it does. What that also means is that this electron pair is going to repel this electron pair a little bit more than the bonding pairs repel each other. And the same thing is true with the non-bonding pair and this bond and this bond. So there is some distortion of the bond angle. We predict the bond angle to be 109.5 because we had 4 EDs, 4 electron domains. But in reality, the bond angle is a little bit less than that. Not much, guys. You know, maybe it's compressed, a degree or so. Now, the molecular geometry has a new name here. In naming the molecular geometry, we want to ignore with our mind's eye the lone pair. The geometry is just dependent on the atoms and the bonds they have with each other. The name of this geometry is Trigonal Pyramidal. Can you see it's like a pyramid or a camera tripod, the base of which is a triangle. I don't know how to turn this for you best to see it. The base is a triangle, and then it comes up to the top of the pyramid. Trigonal Pyramidal. I'm hoping if you're doing this with marshmallows at home, you can see what I'm talking about. All right, let's put that one aside. And the next structure that I'd like you to draw is that of water, H2O. So draw your Lewis electron dot diagram for water. Pause the video if you need to. And this is what you should have drawn. So we're going to focus again on the central atom and count how many electron domains surround the central atom. Now remember, electron domains are either bonding pairs or non-bonding pairs. Can you see that the central atom here, the oxygen, again, has 4 electron domains. So that means that you're going to grab your marshmallow and 4 toothpicks and orient your 4 toothpicks in the tetrahedral arrangement. That's the geometry that gives the best bond angles. And we predict that the bond angles would again be 109.5. However, out of those 4 electron domains, only 2 of them are bonding pairs, and the other 2 are non-bonding pairs. Now, notice when we draw a Lewis structure, it looks like they're across from each other, but when you do your tetrahedral shape, there's really no across from each other. No matter which 2 toothpicks I choose, they end up being next to each other. Again, that idea is best seen if you're playing with marshmallows or gumdrops or grapes and toothpicks. All right, so we have here the tetrahedral geometry as our starting point with predicted angles of 109.5. But these 2 lone pairs really repel each other, causing the bond angle to distort even more than when we had only 1 non-bonding pair. So as we name the molecular geometry, again, in your mind's eye, you're ignoring the lone pairs and you're just looking at the atoms. 2 H's and an O for water. And the name of this molecular geometry is the very scientific sounding bent. This is a bent geometry. The bond angle is a little bit less than 109.5. So our predicted bond angle, 109.5. In reality, it's a little bit less, not much, maybe a couple of degrees. All right. Now I want you to draw the electron dot diagram for fluoron trifluoride, BF3. Again, pausing the video if you need to take a minute to draw that. Here's first step where we add up all the valence electrons. And this is the electron dot diagram that you would draw. Oh, my kitty is mad. Remember, guys, that boron and beryllium never have an octet. So when you draw this, this is the correct answer. Even though boron doesn't have an octet, you would not be moving a lone pair over to become a shared pair. Now, this molecule, BF3, has only 3 electron domains around the central atom. So take a new marshmallow and 3 toothpicks for the 3 electron domains and orient them to give you a geometry that maximizes bond angles. Pause if you need to. And then you should have come up with this geometry. This particular geometry, which gives 120 degrees between electron pairs, is called Trigonal Planar. This one is flat as pancake. It's 2-dimensional. You don't have to try to envision coming out from the surface of the paper. And each of these electron domains is a bonding pair. So the name of the molecular geometry is the same as this electron domain geometry. This molecular geometry is trigonal planar. 120 degrees of separation when you're only working with 3 electron domains. All right, now I would like you to do the electron dot diagram for sulfur dioxide, SO2. Again, pause the video if you need some time. And we're working to me. After I finish teaching, I'll feed you. So we have 18 valence electrons to show in our electron dot diagram. You may have come up with this, or you may have come up with this. And in fact, when we do the formal charges, we find that they're both equally valid electron dot diagrams, which means the true picture is a blend, and we refer to that as resonance. Okay, so you can refer to either one. I'm just going to cover up the bottom one for clarity here. Now again, we're focusing our attention always on the central atom, and we want to count the electron domains. We've seen that a bonding pair is an electron domain, and we've seen that a non-bonding pair is an electron domain. Well, it turns out that a double bond also counts as one electron domain. I know you'd like to think of that as two, but it's not. So this central atom has 1, 2, 3 electron domains. And the Vesper model would tell us that electron pairs want to minimize repulsion to get the maximum bond angle. So 3 electron domains are going to assume that trigonal planar electron domain geometry with 120 degrees between each electron pair. This is a single bond. This one is a double bond. You know, actually, I think I'm just going to make it double bond. There we go. Single bond, double bond, and then our third electron domain is a non-bonding pair. And we have seen in our Vesper model that a non-bonding pair is not in a tug of war between two atoms. So it's free to take up more space. And it's going to exert some extra repulsion between itself and a bonding pair, and between itself and a double bonding pair, which means the bond angle between the two bonds is a little bit smaller than 120. The name of that molecular geometry is also bent, like we saw earlier with water. Remember, water had a bent geometry, but this bent geometry had a bond angle close to 109.5. In this bent geometry, the bond angle is simply a little less than 120. All right, the last example for today, I'd like you to do the Lewis structure for carbon dioxide, CO2. So we're working with 16 valence electrons, and the electron dot diagram looks like this. Central atom, carbon, has only 2 electron domains. Remember again, guys, an electron domain is a single bond or a non-bonding lone pair or a double bond. And for that matter, also a triple bond. A double or a triple bond counts as one domain. So the carbon has 2 domains. If you grab some more marshmallows and toothpicks, Vesper model is going to tell us that to minimize repulsion, when you have 2 electron domains, the geometry with the maximum bond angle is linear. So with 2 electron domains, one electron domain, another electron domain, the predicted bond angle is 180. And because both of these are bonds, when we consider the molecular geometry, we're just looking at the atom to atom to atom And this is very linear with 180-degree bond angle. Okay, that's a lot. So again, the whole idea of molecular geometry is to use the valence shell, an electron pair repulsion model, to predict which geometry gives the maximum bond angles. And it's all going to depend on how many electron domains are on that central atom. In your textbook, you have a table that sort of summarizes what we looked at. When there are 2 electron domains, we predict a 180-degree bond angle. The molecular geometry is linear. When there are 3 electron domains, the predicted bond angles are 120, and the molecular geometries are either trigonal planar or bent, depending on if you have a lone pair or not. And then if you have 4 electron domains around the central atom, the predicted bond angles are 109.5, and the molecular geometry is called tetrahedral if all the domains are bonds. But if you have only 3 bonds and 1 lone pair, it's called Trigonal Pyramidal. And if you have 2 bonds and 2 lone pairs, it's called bent. This bent 109.5, this bent 120. Okay, and the last thing I want to point out is that we've seen that bonds do repel each other, but if you have a lone pair, it's going to repel a bond even more than the bonds repel each other. And if you have 2 lone pairs, they really repel each other, causing the most distortion of all. Okay, guys, I hope that was helpful.